Okay, so last class we finished deriving this sort of abstract multi-objective optimization framework. And what I want to do starting this class is to start instantiating it to get various kinds of guarantees. And as we instantiate it, also come up with algorithms that are maybe more explicitly defined using the structure of the setting we instantiated it. Okay, so if you sort of remember this general multi-objective optimization framework, first of all, the setting was quite general and therefore abstract. We just had like d different like loss functions, and we wanted to make the maximum of them small according to some benchmark. And also the algorithm we came up with, just said like, write down this zero-sum game and like solve for its min-max equilibrium. Okay, so as we start instantiating these abstract loss functions with loss functions encoding the aspects of particular problems we're trying to solve, hopefully that algorithm will also become more concrete. Rather than just saying like solve for a min-max equilibrium of this game, we can start to think about what the min-max equilibrium of this game looks like in our case, and hopefully get sort of algorithms in closed form. Okay, so that's going to be the goal for today. And the first place we're going to try to like instantiate this framework is going to be very familiar. We're going to go back to the sort of standard online linear optimization, expert learning problem that we've been studying from the beginning of the class. And we're going to revisit that setting where now we're going to ask for stronger kinds of regret. Okay, so previously we had been asking for what we called, well, just regret at the time, and that we'll now start calling external regret, which just meant that on average over the entire sequence of play, our cumulative reward was nearly as good as that of the best single fixed action in hindsight. What we're going to talk about today is something I'm going to call subsequence regret, where, like what are the multiple objectives we're going to care about? Well, you're going to tell me some way of identifying different subsequences of play. Okay, so for example, we're going to like recover the standard, like external regret bounds by just sort of instantiating this framework with a single subsequence, including everything. But then we can start getting more interesting things by having more than one subsequence, and these can be intersecting subsequences. So for example, let's think about some things that could go wrong with the standard kinds of external regret bounds we've been thinking about, right? So what are the standard kinds of external regret bounds? Say, it says, if we start running the algorithm on day 1 and start paying attention then, and then we stop running the algorithm at day t and stop paying attention then on average over that whole time period, we have done as well as the best fixed action in hindsight. But what if we start paying attention a bit late? What if we only start paying attention halfway through? Or what if we stop paying attention a bit early? What if we stop paying attention halfway through? There's no guarantee, it doesn't follow from the standard kinds of regret bounds that we will have had low regret on, prefixes or suffixes. It's just something that holds on average over everything. And so one way to try to fix this is to say, look, there's a bunch of subsequences I care about. It's not just the subsequence, the contiguous subsequence 1 through t that external regret speaks to. Maybe for every starting point, little t, and every ending point, little t prime, which defines some interval from t to t prime, maybe I care about the regret I have, even if I like zoom in on that subsequence. Okay, so if I have capital T rounds, there's like capital T squared subintervals, right? And choose t starting points and t ending points. And so I could say, well, maybe I want to have diminishing regret at these root t kinds of rates, not just overall, but simultaneously on every subsequence, for every sort of starting point and ending point. Okay, so that's called adaptive regret, and it's a special case of this kind of subsequence regret we're going to talk about, where the subsequences correspond to like starting points and ending points. Okay, and these are sort of guarantees that are time adaptive. No matter when you start paying attention and no matter when you stop paying attention, the regret guarantee will still hold. There's other kinds of subsequences we could define, right? So maybe every day we're making decisions about people, right? Maybe some person is showing up, we're taking some action, like we're giving them some drug or something. Maybe it's a drug trial. We have to decide whether to give them, which of the drugs, 1 through 5 or a placebo. And a regret guarantee is nice. It says we're doing as well as the best fixed thing overall. But maybe this drug interacts with some of their demographic characteristics, say, right? Maybe it behaves differently for men and for women. Maybe it behaves differently as a function of, your history of diabetes. There might be different sort of attributes that could be medically relevant, but we don't know yet because here we are at the initial stages of the drug trial. And so we might want to have not just no regret overall, but no regret on subsequences consisting of men, no regret on subsequences consisting of women, no regret for people who have a family history of diabetes, or on any other subsequence defined by any demographic characteristic that we think might be medically relevant here. Okay, because it might be that depending on some of these characteristics, we actually want to make different decisions. Maybe the best drug in hindsight is different for different subsets of the population. A standard no regret algorithm would promise nothing of that sort, but if we want promises of that sort, that's called groupwise regret, and that'll similarly be an instantiation of this general kind of subsequence regret we're going to be talking about. And finally, remember we talked about swap regret at the beginning of this sort of part of the course, right? Like this notion of regret that led us in repeated play of games to converge to correlated equilibria. Well, no swap regret, really it was nothing other than saying we have no regret to the best action in hindsight, not just overall, but on the subsequence of rounds for which we've played action 1, and also on the subsequence of rounds for which we've played action 2, and so forth. We have K actions. It was asking for no regret on any of these K subsequences of rounds that happen to be defined in terms of the action that we took on those rounds. Okay, so we're going to want to define a framework for subsequence regret that lets us talk about all 3 of these cases, right? Subsequences should be allowed to depend on time, so we should be able to capture this notion of adaptive regret. They should be able to depend on any externally available features, so they should be able to depend on things like demographic characteristics or things in your medical chart, and it should be able to these subsequences should also be able to be determined by the actions the learner themselves play, so that we can capture things like swap regret. Okay, so that's the plan for today. High level questions? Okay. So let me define subsequent selection and regret. Okay. So let's fix an action space. This is going to be a setup for a standard online linear optimization problem. So we've got an action space A. Let's say that it's K actions. And a context space X. We haven't necessarily had a context space before. These are features that might accompany each day that would tell you things like the patient has a family history of diabetes, or whatever else you think might be relevant. Okay, so before you make your decision on each day, you're going to get features about that day. And now let's say that calligraphic E is a collection of M subsequence selection functions. All right, what is a subsequent selection function? It's just some function that takes as input the time index, the action played by the learner, and any available context, and maps that to a number between 0 and 1. Okay, so maybe it's a binary function. Maybe it maps to either 0 or 1. Okay, think about that as representing whether today, as a function of today's index and the features and the action I played today, whether today is a member of the subsequence or not. Okay, so for these three kinds of regret we talked about, maybe like, for adaptive regret, there's going to be a bunch of subsequent selection functions that are each parameterized by like a lower bound on time and an upper bound on time, like between rounds, 5 and 32, such that if the current index is between 5 and 32, this will output 1, saying that today is a member of the subsequence we care about. Otherwise, it'll output 0. Or for group-wise regret, maybe for every group we care about, like people who have a family history of diabetes, this selection function will actually just look at the context X and output 1 if the person has a family history of diabetes and 0 otherwise. Or for swap regret, there'll be a subsequent selection function for each action, and it'll output 1 if we played action 5 and 0 otherwise. Okay, it's just indexing whether each subsequence is active, and this is a collection of such functions. And actually, there's no reason to limit this to just outputting a binary value, 0 or 1. It can output a real value, which you can think of as encoding fractional membership in the subsequence. Question?
So for the action, is that only the preferred period action, or does it can it be like last if the all parameters are played?
Yeah, so it can depend on that too. If you like, if you like, I could, rather than writing this as a function of time, I could have written it as a function of the transcript.
Okay.
Sort of without loss, since there's going to be no constraint on what the context looks like. If you want anything that came in the past is just like encoded in the context. So yes, like another valid kind of subsequence would be, the set of days that come after, me accidentally killing a patient by giving them the wrong drug, things like that. Yeah, so the subsequences can depend in arbitrary ways on the past as well. The only thing they cannot depend on is what happens today, the thing that hasn't happened yet. Like I need to know whether today is a member of the subsequence before I observe what the adversary does today, what the cost function is for today. Other questions? Okay, so that's a subsequent selection function. And then, like play proceeds as we're used to in an online linear optimization problem. So in rounds from little t equals 1 to capital T. The only new step really is that the learner observes context. So the learner observes some context, xt, from the context space chosen by the adversary. Okay, so the adversary gets to decide what the features are each day, but the learner observes those features before they need to make their prediction. Then the learner chooses a distribution over actions. Okay, so chooses some distribution PT over their action space. Then the adversary chooses a cost vector. As usual, each cost will be bounded between 0 and 1. There's a cost for each of the k actions. And the learner experiences expected cost, which is just the inner product between the distribution they chose and the cost vector. Okay, so the standard, oh, yeah. It's just in X. This just says X. There's K actions, and so it's 0, 1 to the K. For each one of the K actions, they tell me what the cost is. So I choose a distribution over K actions, they tell me. Oh, you know, who knows what the context space looked like? It could be like a photograph, or it could be pages of medical records, or this is just like the information that we have available. Somehow the relevant computation to parse the information into what we care about, it's going to be encoded in these subsequent selection functions. They're going to take as input context, whatever that means, and then tell us for the subsequence they are concerned about is today relevant or not. There's M of these things. Yeah, like ultimately there's sort of M bits we care about as a function of the action we play, the context, and anything that's happened in the past, say. But the context could be anything, right? So these events that we're defining are not necessarily exhaustive. Like we could add more of them, for example. Yeah. That's right. So that's what's important, actually. So, right, like the subsequent selection function can sort of depend on anything either that you've already observed to the past or today's context, or that you control the action you take. It can't depend on stuff that you haven't seen yet or that is not under your control, like what the adversary is going to do today. And that's going to be important as we see when we like think about what the algorithm should look like, exactly because as you're thinking about what action to play, you will be able to think about what that does to, you know, whether today is a member of the subsequence or not, and subsequently what that does to the regret on that subsequence, which we'll define shortly. That's right. Yeah. So like, and it's sort of like trivial counterexample. So like, suppose what's happening is I am, you know, you're flipping a coin and I'm trying to like guess if it's heads or tails. Okay, so the kinds of things I can do, or I can make sure I've got no regret guessing, you know, whether your coin is heads or tails, like when it's raining or when it's not raining. I can have no regret on the subsequence of rounds for which I guess heads, for which I guess tails, but I can't have no regret on the subsequence of rounds for which the answer is heads and which the answer is tails, because the only way to do that would be to guess perfectly every time. Okay, so like somehow, I could get one of them, but not both of them at the same time by always guessing heads. Yeah. So like, yeah. So like basically, yeah. For most questions I have about this kind of thing, the answer is revealed either by thinking about playing rock paper scissors or by thinking about guessing a coin flip. And yeah, in this case, like if you could have no regret conditional on the outcome, then that would imply you could guess a coin flip perfectly every single day, and you can't do that. Exactly. That's right. So conditioning on the adversary's outcome, that's too hard. Yeah.
Selection functions, do they have to be, first of all, do they have to be comprehensive?
Not necessarily, although like, you know, they may as well be. Like if there are days for which none of the subsequences can be active, you know, you'll see when we write down what our objective is in terms of subsequence regret, but like, you know, we're just like, nobody's paying attention on those days. You could just do whatever you want. But like, you know, I think it's helpful when we do this to think about that, you know, we're always, it's helpful to think about us always asking for something strictly stronger than what we've done so far. Okay, and one way to make that precise is to say that this collection of subsequence indicator functions, it always contains the function that is the constant one function that identifies everything as a subsequence. That'll just be like external regret. And so we're always going to be asking for external regret plus regret on some other subsequences. Although strictly speaking, as I've written these things down, it could be that like, you know, nobody's paying attention on even days or something, in which case, you know, like do what you like on even days, nobody will care. They can overlap, yeah, that's going to be important. If they couldn't overlap, there would be an easy solution to this problem, which is to run, or you know, okay, sorry. If they couldn't overlap and they didn't depend on your own actions, there would be an easy solution to this problem. If every day, you know, say there's m subsequences I care about every day, just by looking at the, you know, context and available at that day, and not worrying about what action I play, I could assign that day to exactly one of these subsequences. I could initialize a copy of multiplicative weights whose job it was to get no regret on each of these subsequences and just run the corresponding copy on the day that corresponded to that, so on each day corresponding to that subsequence. So that would sort of work if the subsequences didn't intersect. But that is going to break. Like that's not going to make sense if the same day can be a member of multiple subsequences, and that's when we're going to need these sort of more sophisticated techniques. Good question. Other questions? Okay. Okay, so what's like the goal in this setting? So let's fix the transcript. Pi t. And what does a transcript record in our setting? Well, every day it records a context, a distribution of our actions, and a cost vector. The expected regret to action I on subsequence E is, we'll write it like this, the regret, depending on the transcript, the subsequence, and the action, is just the sum over all of the days of the expectation over the action we play. So the action we play, J, is drawn from the distribution over actions that we chose that day. Of the indicator function for whether subsequence E is active that day. This depends on the context, the time, and also the action that we choose that day. Of the difference between the cost our algorithm actually experiences, well, if we chose action J, that's cost J minus the cost our algorithm would have experienced had we played action I. Okay, because this is the regret to action I. Okay, so this is our regret to action I on the subsequence defined by this subsequence selection function E. Okay, so basically, if E is an indicator function, 0 or 1, then we're not really summing up over all of the days. We're summing up only over those days for which that subsequence is active. And if it's a more general subsequent selection function that's not binary valued, you can think about this as like a weighted sum over the days, where this subsequent selection function is the thing weighting the days. Okay, like for regular old regret to action I, that would just be like this quantity, except without the subsequent selection function in here. And we'll say that the learner has E subsequence regret bounded by alpha if, when we look at the maximum over all events, and also the maximum over all of our actions, over all of those, the maximum regret on the transcript to event E and to action I is not more than alpha. Okay, makes sense. So regret to action I on a subsequence is just the regret, except rather than summing up over the whole, all of time, we sum up only over those days that are a member of the subsequence. Okay, that makes the most sense if the subsequence just depends on time, like for adaptive regret, like regret between rounds 27 and 92, or if it depends on the context, like regret on people who had a family history of diabetes. If it depends on the action we chose, like days we played action 5, it doesn't quite make sense to directly say sum up over the rounds that are a member of that subsequence, because like the subsequence depends on what we choose, and that's sort of why this indicator function is inside the expectation, right? Because like if the subsequence depends on the action we choose, then it is depends on, well, the expected regret depends on the probability that we choose that action. Okay, but basically, these are all measuring regret on the same subsequence, but weighted in different ways. We're weighting the days that the subsequence indicator function cares about highly, the others not, and we want the maximum over these quantities should be small. Good. Yeah, so the question is like, are we like does anything go on like short subsequences? And okay, for the bounds that I'm going to show you in class, the answer is basically going to be yes, which is that, the kind of thing we're going to show is that we can bound subsequence regret for any collection of subsequences by something like root T, root capital T. Okay, it's the same kind of bound we got for multiplicative weights on the whole thing, but like now, like root T was like a really good bound when the sequence was of length T, but like if we're only summing up over subsequences, like root capital T becomes a progressively less good bound as the subsequence length gets smaller. In particular, it's like vacuous if the number of days that are a member of our subsequence is like less than root T. So what we're going to do today is get like a root T bound. And so you're correct in saying that, like, basically, yeah, like there's two ways to like pass this test on a subsequence. Either we have to do relatively well on the subsequence, or the subsequence has to be short. It has to be, like, in particular, our bounds are going to be like vacuous for subsequences of length smaller than root t. Now it is possible, using very similar techniques, to get stronger bounds where basically, rather than uniformly bounding the regret on every subsequence by root capital T, what is possible to do is to bound the regret on a subsequence of length, on a subsequence E of length TE by root TE. So it is possible to get bounds that simultaneously bound the regret on every subsequence as a function of like root the length of that subsequence. And so it will still be the case that the bounds get better for longer subsequences, but the bounds will generally be non-vacuous, like always, or maybe, there will be constants that will cause constant length subsequences to have vacuous bounds. But like, that's right. Like basically, just to like pull on this thread, what are we going to do here? We're going to basically pretty directly reduce this to this AMF regret framework we derived last class. And there, what we derived is root capital T bounds on the worst of these coordinates. Where did that come from? Well, it came from the fact that basically when instantiating this general AMF framework, remember there was like a no external regret algorithm that we used as a subroutine. We just used exponential weights, which had a root T regret bound. But if you plug in fancier no regret learning algorithms that have regret bounds that are sensitive to the reward sequence, and such things exist, you get more sophisticated regret bounds out the other side of this like AMF framework. And if you use the right ones, you can get root little t here. Yes. So anyways, to answer your question, for what we're going to show in class, basically the bounds will be vacuous for any subsequence of length smaller than root capital T, but that is not necessary. In general, it is possible to sort of up to like constant or log terms, like to get optimal regret bounds on each subsequence compared to like what you could have done if you had known what was a member of that subsequence ahead of time and run an algorithm just on that subsequence. Well, what weight would you pick? I guess the tricky thing is that there's not just one subsequence you care about. Like if there was just one subsequence you cared about, you could just weight the actions and feed them to multiplicative weights. Like you say, I care about my regret, not overall, but just on like days that are a multiple of 7. And I'll, anything that's not a multiple of 7, I'll just like throw it away. I'm only going to feed multiplicative weights every 7th example. That would give you subsequence regret on days that are a multiple of 7. But it would not give you subsequence regret on days that are a multiple of 5.
Well, then you just wait like 7, day 7, day 5.
Well, if you did that, you'd have no regret on days that were either a multiple of 5 or a multiple of 7. But it's not clear you'd have no regret on days that were a multiple of 7. Right? Like the reason this is going to be interesting and something that would be hard to achieve just by some straightforward weighting that you feed to multiplicative weights is that different ones of these subsequences weight the time periods differently. Right.
If you have no regret for both days 5, otherwise it would.
But you don't have no regret for both day 5 and day 7. But like already, like suppose I just run multiplicative weights. I have no regret over the whole sequence from day 1 through t. So it sounds like you're coming very close to saying an argument that would translate into, therefore, because the set of all days includes multiples of 7, I have no regret on multiples of 7. But that's not true because basically because regret can be negative, right? So it might be that I have no regret overall, but the way that I have no regret overall is I have high regret on days that are multiples of 7 and negative regret on days that are multiples of 5, and that somehow these cancel each other out. But I want low regret everywhere. Does that make sense? Yeah. Yeah, like good. So like an important thing to understand, I think, to avoid these yeah, otherwise sort of contradictions is that regret is, like we want regret to be close to zero, but that doesn't mean that it can't be negative. And it can definitely be negative when I start conditioning on subsequences. But like, in particular, to go back to this like coin flipping example, like for anything reasonable I can do, if I look at the subsequence of days for which the coin came up heads, I will have, okay, I should have very positive regret on that subsequence. But if I look at the subsequence of days for which I guessed the right answer, I'll have zero regret. It is possible to get negative regret though.
You can't condition what is different, I guess. That's like.
Well, that's right. I'm not allowing this in this framework, but I think it's relevant to your argument.
Okay.
Natalie.
So if there are no overlap, like you said, like then this is easy because it's sort of like we can run, exponential waves like that with on all.
Mm-hmm.
And it's the whole overlap.
Then it's just one subsequence, yeah.
Part that's sort of not trivial is when there's like partial everything sort of partially overlap.
That's right. It is the overlaps. It is non-trivial overlap structure that makes this interesting and non-trivial. Other questions? Okay. Okay. And just in terms of terminology, it's going to be worth making a distinction whether these events actually do depend on the action or not. I've allowed them to depend on the action, right? We're going to need that when we derive things like no swap regret algorithms. But the world will be somewhat easier when the events don't depend on the action. And so for subsequent selection functions that happen not to depend on the action argument, I'll call those action-independent subsequences, and we'll have a simpler algorithm to get no regret for action-independent subsequences than we will for subsequences that can depend on the action. Although the regret bound is going to be the same. And in fact, like both of them will really just be instantiations of this AMF framework. So in some sense, the algorithm is the same, compute the min-max equilibrium of some game. It's just that what that min-max equilibrium looks like, it's going to be a lot simpler when the actions don't depend on, when the subsequences don't depend on the action. So it just sort of heads up, it's going to be useful for us to have that distinction in our mind. Action-independent subsequences versus the general case when the subsequences can depend on the action. Okay. So let's remember this sort of general multi-objective optimization game that we sort of analyzed and solved last week. Okay, so remember in the general multi-objective optimization game, an adversary for us defines like an environment every round that gives us an action space. It gives the adversary an action space. And the adversary tells us a loss function in each of D coordinates. And we play an action, the adversary plays an action. Loss is accumulated in each of these coordinates. And in the end, the thing we know how to control is the value of the accumulated, the value of the maximum accumulation of all of these coordinates. Okay, we control it by what we called the sum of the adversary moves first values. Okay, so I want to use that framework to solve this problem. And so what I need to tell you next is what is the multi-objective optimization, how am I going to instantiate the multi-objective optimization game to handle subsequence regrets? Okay, and I'll do so in sort of the obvious way. Okay, so the construction is very straightforward. Okay, so I'll call this the subsequence regret multi-objective optimization game. Okay, and this is a particular instantiation of the general d-objective, multi-objective optimization games we solved last week. Okay. So, we're given M subsequences E and K actions. And we're going to define a d-dimensional multi-objective optimization game where the dimension is going to be M times K. Okay, so we're going to have one objective value for each event cross action. Okay. And so in this case, the action space for the learner and the adversary, although in principle those could change from round to round, in this case, they're going to be the same every round. Okay, so the action space for the learner at each round T, those are just going to be the set of distributions over their K actions. The actions for the adversary, those are just the set of cost vectors, okay, K-dimensional cost vectors. Okay, and note that these action sets are, finite dimensional, convex, closed, everything we needed them to be. Okay, and now we need to define the loss increment functions. So for each subsequence and for each action, we define a corresponding loss increment at round T for that subsequence and action as a function of the distribution played by the learner and the cost vector played by the adversary. Just so that it corresponds to the sort of teeth term of the sum that's going to measure for us the subsequence regret to action I on subsequence E. So it's just the expectation over an action drawn from the learner's distribution of the subsequence indicator function evaluated at T, J, and XT. Okay, sort of the round and the context for that round are just like sort of baked into the environment that the adversary is revealing to the learner in the AMF game at round T. And the other argument, the distribution on actions played by the learner, that's the move that the learner plays at this round of the game with the adversary. Okay, so the subsequence indicator function times the difference between the cost the adversary plays at round T in action J for action J and the corresponding cost for action I. Okay, so this is the construction. Let's just sort of observe that we've followed the rules for these multi-objective optimization games. So we already saw with the action spaces for the learner and the adversary, they're closed, convex, finite dimensional. This loss function, remember it has to be convex in the learner's action, concave in the adversary's action. Well, actually, it's linear in both of them. right? It's sort of transparently linear in the adversary's action. And in the learner's action, well, they're playing a distribution, and this is an expectation over this distribution. So it's linear by linearity of expectation. Okay, so this is a legitimate, d-dimensional multi-objective optimization game. We have a general algorithm for playing in games like this. The construction makes sense. Okay, so what we need to do, two things. So first, we need to sort of instantiate the general theorem that we proved for AMF regret for this particular instantiation of the game. Okay, so we've got like a regret bound that we can read off in terms of the adversary moves first values of the game. We need to establish what the adversary moves first value is for this game in order to read that off. And then we need to come up with like an actual algorithm that realizes that bound. Of course, we've got this generic algorithm that just solves for the min-max equilibrium, but like maybe in this case, we can simplify the algorithm using the particular structure of the loss functions. Okay. Mm-hmm.
So when you think about the adversary when
What is chosen by the adversary?
the context.
Yeah, the adversary chooses the context. Basically, adversary chooses everything except for what you do. Okay. Okay, so what's the theorem? Fix any M subsequence selection functions E and any set of K actions our AMF algorithm, in particular the one instantiated with exponential weights that we derived at the end of last class that has a concrete regret bound. Our AMF algorithm run on this game on the subsequence regret multi-objective game. Guarantees that when we look at our subsequence regret, the maximum over all of the subsequences and over all of the actions of our regret on that subsequence E to that action I, that this will be guaranteed to be at most 4 times the square root of T log M plus log K. Okay. So just looking at this bound for a moment, if we were just asking for external regret, like regret over the whole subsequence, over the whole sequence, and we were running something like multiplicative weights or exponential weights, we would get something like root T log K. Okay, so now we are asking for regret, not just over that subsequence, yes, but also over all of these other M subsequences. And it's saying we're controlling the maximum regret over all of those subsequences at the same time by a very similar looking expression, an expression that's just larger by this log M term, where M is the number of subsequences. So it's saying we can get no regret simultaneously on all of these subsequences. And we get basically the same bound that we get with multiplicative weights, worse only by a logarithmic term in the number of subsequences. Okay, so like, like you could have nearly exponentially many in T subsequences and still have this be a non-trivial bound. Okay, does that make sense? In particular, like these kinds of subsequences we've been talking about in this class so far, like subsequences on all, no regret on all contiguous intervals of time, for example. There's only like T squared of those. So like doing that will cost us only like a log T term on top of regular regret. Or, no regret conditional on features that we think might be medically relevant in a clinical trial setting. Well, maybe we don't know what's medically relevant, but like let's throw it all in. We're only going to pay logarithmically for the number of things we think might be relevant, and in exchange we'll get a strong regret guarantee for that subsequence. Or regret conditional on the actions we played. Well, there's only k actions, so and we're already paying a log k term. It's only going to cost us another factor of 2 in here. Okay, so it's a pretty strong bound that we pay only a log term for the number of subsequences.
Okay, so if m is like say m is just equal to, right? Like the advice bound is different. But it happened to be that the way that we're assigning context is that like it was a different context every round, exactly one context, right? Now, really, I mean, like what's really happening is because you have what you want on every.
Yeah, you're saying like this bound wouldn't be so interesting if we had like T subsequences of length 1, because the subsequence regret bound would sort of be like vacuous in that case. Yeah, so like, that's right. So we can handle lots and lots of subsequences, no problem, but on a particular subsequence, the bound we've given here is only interesting if that subsequence is like kind of long, like it had better be longer than root T. Now, by the way, because these subsequences are allowed to intersect, there's no contradiction, right? Like you might be worried that if these were disjoint subsequences and the bound is only interesting for like subsequences of length root T or longer, that there's only, root T many distinct subsequences, but that's not the case here. You could have exponentially many subsequences that all had length roughly T over 2. But it's a good point that a bound like this is only interesting for like sufficiently long subsequences. And it's related to the question you asked initially, which is that this bound is in fact improvable where this root T can be replaced by root length of that subsequence. And so it would be non-vacuous for any subsequence that was sort of long enough so that like this 4 on the log terms, gave you something that was like less than the length of the sequence.
You're still like, I mean, like what do you really expect to do if you have just like T different?
It's always going to be vacuous if every subsequence is of length 1.
Like both about like right. There's like something about like if you have depending on the way that the actual subsequences are structured, like there can be like a technically like performance in meaningful and bound.
That's right. Yeah. So like, yeah, this implies, non-trivial performance on a subsequence only if that subsequence is long enough to make the right-hand side, like non-trivial. Good. Other questions? Yeah.
What about context dominations of subsequences?
You're saying if I have no regret on a bunch of subsequences, do I also have no regret on any subsequence selection function that is like in their convex hull? I think so, because yeah, like if my regret on a convex combination of subsequences should be a convex combination of my regrets. And so if they're all less than alpha, that'll also be less than alpha. Yeah, so if you think about, yeah, like, really, when I say you get no regret on any of these subsequent selection functions, I've left out that you also get no regret on anything in their convex hull. That's true. Conceivably. Yeah, that's true. That's a useful thing to keep in mind. Yeah. I love these questions that begin with like, the theorem is great, by the way. Go on.
The regret guarantee is that you're not just getting close to the answer, so you're sort of getting the best, like round by round. But that's really thing. What if you had n of this really close to exponential, but just not of the exponential? What happens? How close are you getting to this possible thing of that's just possible?
Right. So let's see. So yeah. So let's see. So let's go back to this like coin flipping example where we're like, oh, like, why don't I just try to get no regret conditional on like the coin being heads and conditional on the coin being tails? Well, that's clearly impossible because like conditional on the coin being heads, the best action in hindsight was heads, and conditional on the coin being tails, the best action in hindsight is tails, and the only way to get no regret is to perfectly guess these things. And good, that's not allowed here. Now, you might now say, okay, well, fine, that's not allowed. I can't condition on the coin being heads or the coin being tails. I'm just going to ask for subsequence regret on every possible subsequence, like we're going to play this for t rounds. There's 2 to the t subsequences of days. And whatever happens with the coin, ex post, one of those subsequences will be the one for which all the coins were all heads, and the other of them, and another one will be the one for which the coins are all tails. And now I like got away with asking for no subsequence regret conditional on the coin being heads and conditional on the coin being tails, and I did it without depending on A. And yeah, like that's not going to work, because if this is 2 to the t, then log of 2 to the t will be t, and so we'll have root t squared, which is t, and so it'll give a trivial bound. And this is but right, like what you're sort of observing is that you can get almost that far. Like you can get no regret on t to the alpha many subsequences for alpha strictly less than 1, because log of that will be like alpha. Or yeah, 2 raised to the t to the alpha, because log of that will be like t to the alpha, and you'll have t to the 1 plus alpha here over 2, which is going to be like strictly sublinear, so non-trivial. And so I guess if you wanted to, you could sort of relate this to tight concentration bounds for Bernoulli random variables. Flipping a coin, what is the I don't know, maximum number of heads that I would get on any predefined subsequence of from some collection of t to the alpha subsequence or 2 to the t to the alpha subsequences, and there would probably be concentration inequalities that would were they true, lead to contradictions here. So there's probably a relationship between the kinds of obtainable regret bounds you can get and just probabilistic statements about coins. Exactly. Like basically, like just like as a sanity check, we better not get regret bounds that tell us we have an algorithm for perfectly guessing a coin flip every day. We also shouldn't have regret bounds that are going to like invalidate probabilistic concentration inequalities. Exactly. But it's like reassuring that we're getting something like the right answer, that when we try to cheat and be able to perfectly guess the outcome of a coin flip by asking for all 2 to the t subsequences, that is sort of, first of all, that the bound becomes vacuous then and we can't get it, but also that it just barely becomes vacuous, that somehow we haven't proved a regret bound that is we couldn't substantially tighten this, right? If we tightened this by if we tighten this in any sort of significant asymptotic way, right? Like if we replaced the square root somehow with a lower power, then all of a sudden your trick would allow us to guess the outcome of a coin. That better not be possible, right? So what you're describing is also some kind of, right, like that'll yield a lower bound on what this can be. Good question. Other questions? Okay, let's prove the theorem. Okay, so first of all, let's just remember like what we're trying to do here. So we've got a generic theorem for the kind of adversary moves first regret we can get in multi-objective optimization games. We have a particular multi-objective optimization game. We need to instantiate that theorem. That theorem compares, when it tells us something about AMF regret. Well, what is AMF regret? It's telling us how much worse we are doing cumulatively in the maximum coordinate of these D objectives compared to what we call the adversary moves first value of the game. So the thing we care about here is exactly the maximum value of these m times k objectives we've defined. But like, there's no adversary moves first value on the right-hand side. So like in order for this to fall out of the theorem we proved, it had better be that the adversary moves first value of the game is 0. Okay, so that's the first thing to establish. All right, so a lemma. In every round of this game, for all t, the adversary moves first value at round t is 0. All right, so given a cost vector by the adversary, so given a cost vector chosen by the adversary, remember when we were thinking about the adversary moves first value, well, the adversary moves first, so we know what their cost vector is, and only then do we need to come up with an action to play. So given such a cost vector, let's let I star of c be a coordinate of that cost vector that minimizes the cost. It's a minimum value coordinate in that cost vector. All right, and let's let P of C be, like the vector, like the probability distribution that just places all of its weight on that minimum coordinate. So it's just like a standard basis vector that has a 1 in this minimum value coordinate and a 0 everywhere else. We're just deterministically playing the action that corresponds to minimum cost in the vector chosen by the adversary. Okay, so what is the adversary moves first value of the game? Well, by definition, it is the maximum overall cost vectors chosen by the adversary of the minimum overall distributions chosen by the learner of the loss experienced in the maximum coordinate, which in this case is the maximum over events and indices I, of the loss in that coordinate when the learner plays P and the adversary plays C. That's just the definition of the adversary moves first value. Adversary first picks a cost function, then the learner moves and best responds, and we measure our performance by looking at the maximum coordinate. Well, you know, the max min value is at least what the learner would obtain if they use this particular strategy, right? We're minimizing over all strategies. So it's at most the maximum over cost vectors, events, and indices of the loss increment in index EI when the learner plays the distribution P of C and the adversary plays C. Okay, like we've just replaced this min with a particular choice of the learner, and so all that's left is we're maximizing over everything else in the expression. Well, what is this? It's the maximum over C, E, and I of, well, what is this loss function? The event selection function, the subsequent selection function, instantiated at T, that's the time step, I star of C, that's the action chosen by the learner deterministically in this distribution, and whatever context we have available today of the cost at index I star of C minus the cost in index I. Okay. Now, who knows what this thing is? Like, we didn't choose our action by looking at this subsequent selection function at all. So this first term, it could be anything, but it's non-negative, right? Because by definition, the subsequent selection function is like, gives you a number between 0 and 1. And what's the second thing? Well, it's non-positive because I star of C is by definition the minimum coordinate value of C. And I is just something else. So if we take the minimum value in any coordinate and subtract some other coordinate value, could be 0, could be negative, definitely not going to be positive. Okay, so we have a non-positive number times a non-negative number. So it's at most 0. Okay, so the adversary moves first value of this game is at most 0. We might just, like we no longer need the min-max theorem because the min-max theorem is like baked into the AMF regret bound we're using, right? But like, isn't it convenient that we only need to think about how well we could do if we knew what the cost function was before we had to move, right? Like, no thought is required here. Like, we're just like, oh, let's play the action that has lowest cost, and like, we've bounded the adversary moves first value of the game, and now we can plug that directly into our theorem. It's also exactly 0 because the adversary could pick cost vector equals to 0. Yeah, if it was better than 0, then actually we'd get a better regret bound than this, which we know is not possible. Okay. So then our final regret bound, the statement of our theorem, is just going to come from plugging in the generic bound we have for AMF multi-objective optimization with this AMF value. All right, so what is our regret? Thing we want to bound our regret to subsequence E and action I. Well, it is just the sum over all of the rounds of the expectation of the action we choose at that round of the subsequence indicator at that round times the cost in the jth coordinate minus the cost in the ith coordinate. Well, this is exactly what we've cooked up to be the sum over all of the rounds of the loss in this multi-objective optimization game in the coordinate of the loss indexed by the event and the action. Which is exactly equal to the sum over all of the time steps of the loss in this coordinate of the multi-objective optimization game minus the adversary moves first value at that round, because the adversary moves first value is 0. And this is the thing, this is the quantity that generically we proved a theorem about last class. This is the definition of the adversary moves first regret exactly upper bounds this quantity for every coordinate of the loss function. And so just instantiating our theorem from last class, this is less than 4 root t log of m times k, okay, which is the bound we have there. Okay, so this is literally just a direct corollary of the general multi-objective optimization framework, instantiating it with this multi-objective optimization game and observing that the adversary moves first value is 0. Make sense? Okay, so if we didn't care about closed forms for algorithms, if we just cared about, like bounds, and we even have a general algorithm in principle that just tells us at this point compute a min-max equilibrium, we would now have an algorithm for all the kinds of regret we talked about, right? We have an algorithm for swap regret, right? Just by instantiating this. We have an algorithm for subsequence regret. We have an algorithm for groupwise regret. That all follows directly from the AMF framework. And to get the regret bound, just count the number of subsequences, and it shows up under this log. Okay, so in principle, we've now derived all of these different kinds of regret bounds. And maybe the only thing that remains to do is to get more insight into algorithmically what's going on, because right now our algorithm just says, write down this abstract game and solve for a min-max equilibrium, which is maybe in generality in this abstract setting the best you can do in terms of describing this. But now we've got a particular game, and it might be that the min-max equilibrium that we need to compute at every round for this game has some nicer structure. Okay, questions? Okay. And so this is where, remember at the beginning of class, I sort of said it might be worth mentally making this distinction between subsequence indicator functions that depend on the action for things like swap regret, and those that don't, which I called action-independent subsequences for things like, adaptive regret or group-wise regret. And basically, yeah, like where this becomes relevant is exactly trying to take our general algorithm for AMF regret, which just says compute a min-max equilibrium, and trying to sort of instantiate that with a particular, closed form for what the equilibrium looks like. The equilibrium is simpler if the subsequences are action independent. Okay, so let me write down the algorithm for action independent subsequence regret. And we can stare at it for a moment and see what it's doing. It's going to be doing something, kind of intuitive when the subsequences are action independent. It's going to be doing something somewhat less intuitive when they're not action independent. Okay. And maybe first, it's just helpful also to remember what the generic algorithm was, right? So the generic algorithm, remember, it was running a no-regret algorithm like exponential weights over, in this case, the m times k loss functions. Okay, so every round we'd have some weighting of these loss functions, and we would solve a zero-sum game whose objective was the weighted sum of these loss functions, where the weighting in the weighted sum at every round came from the multiplicative weights distribution. So we were like running a copy of multiplicative weights kind of in the background that was being used to define the objective function in the zero-sum game that we were computing a min-max equilibrium for. Okay, so maybe unsurprisingly, there will be things here that look like multiplicative weights kind of weights. The difference is there will be no step in this algorithm that says compute a min-max equilibrium. Like the weights I'm going to write down in this algorithm are the min-max equilibrium. All right, so we're given a set E of M action independent subsequent selection functions. Okay. And then at each round, first we observe the context. Okay. So remember, these are action-independent subsequent selection functions. So we know, what round it is, and once we know the context, we now know exactly which subsequent selection functions are active and which are not. In general, we wouldn't at this point. We wouldn't until we chose our action, right? So in general, there would be this sort of self-referential aspect where in choosing our action, we are defining which subsequences are active. But if these are action-independent subsequences, at this point, at this moment, after we've observed the context, before we need to choose an action, we know exactly which ones are active and which are not. We're going to use that. And we'll define the following distribution over actions. The weight that we put on action I, it's gonna be a little complicated, so I'll write a big old expression here, but it has a simple interpretation. It's the sum over all of the subsequent selection functions of the evaluation of that function. It's action independent, so it takes as input only the time step and the features of the exponential. This is where we're seeing like an exponential weights kind of expression the exponential of the subsequence regret to action I that we have experienced historically. Okay? So the sum from rounds t prime ranging from 1 to t minus 1, so just historical loss here, everything in the past, of the indicator for whether this subsequence was active at round t prime in the past, times the regret we had to action I, which is just the loss we actually experienced at round t prime minus the loss we would have experienced had we played action I at round t prime. Okay, this is the weight we're putting on action I. This has to form a probability distribution. And so we just have the normalization term in the denominator. So the same thing, except summed over all of the actions j. So the sum over all of the actions j of the sum of the events of the indicator that that event is active today times the exponential of the historical regret we have had to subsequence E and action J. Okay. And then we don't just define that distribution, that's what we play. Okay. Okay, so first of all, like these sort of simple algorithms we studied at the beginning of class, like multiplicative weights, exponential weights, and unlike this sort of general AMF thing, there's no equilibrium computation going on here. There's no step of this algorithm that's like solve for a min-max equilibrium. I've just defined a distribution. It's like a little bit more complicated than the multiplicative weights distribution, but not that much more complicated. It's something you can write down. It's something you could just compute in, you know, closed form and have sort of simple updates to. So this would be easy to implement. Okay, there's no optimization step here. And you just play that distribution at each round. Okay, what is the distribution? Well, like what we're keeping track of, basically, is for each subsequence selection function, and for each action I, what is our running regret on the days when that subsequence was active to action I? Okay, so if there's, you know, k actions and m subsequent selection functions to like implement this thing, we could just keep track of, you know, m times k running sums, and every day update that by just adding today's term to each of those sums. Okay, so we're just keeping track of our historical regret on each subsequence. Okay, what do we do? Well, we basically, for each subsequence and for each action I, come up with something that looks like a multiplicative weights distribution on that subsequence. If that was the only subsequence in the world, if we were just running multiplicative weights on that subsequence, what would we do? We would basically weight each action proportional to like the regret that we have to that action. Okay, this is kind of like maybe what you were suggesting at the beginning. If there was only one subsequence, we could just like run multiplicative weights, having weighted that subsequence. The difficulty is, of course, that a particular day can belong to multiple subsequences. Okay, so we basically have a multiplicative weights distribution for each subsequence. It's like the distribution you would get if you were just running multiplicative weights on that subsequence, except it doesn't make sense to run multiplicative weights on each subsequence because there will, you know, like when a day arrives that's a member of multiple subsequences and these two copies of multiplicative weights that both apply to today recommend different things, you know, what do? Right? You can't literally run multiplicative weights on each subsequence. Well, here's what you do. You take all of the subsequences that are active, only the ones that are active, not the ones that are not active, and you sum together their distributions. You take the multiplicative weights distribution maintained for each subsequence, you select only those subsequences that are active, and you sum together those distributions. And now you don't have a distribution anymore, but you just renormalize. And you play that. Okay, so you just, it's sort of like you're running a copy of multiplicative weights separately for each subsequence. When the day comes that more than one of them apply, you just sum them all together, renormalize, play that. Okay, and more generally, remember, these subsequence indicator functions, they don't have to be binary valued. It's not saying today is a member of the subsequence or today is not a member of the subsequence. They could, they're numbers between 0 and 1, and so that in general you take a weighted sum of those multiplicative weights distributions. Okay, so very simple intuitive algorithm actually that gives regret on all of the subsequences. It is very important in this algorithm, or in order for this to even make sense, that these are action-independent subsequences, right? Because in the description I just gave you of what you do, you look today at all of the subsequences that are active, you select out those multiplicative weights distributions, and you sum them together, and that's what you do. But if the subsequences depended on the actions that you played, then there would be this self-referential thing, like which subsequences are active depend on which action you play, but what action you play depends on summing together the distribution on these different subsequences that are active. So there's this sort of circularity here, which is why what I've written down here only makes sense for action-independent subsequences. Okay? So next class, we will prove that for action-independent subsequences, the algorithm over there gets this regret bound, okay? We'll prove that by just showing that actually this is the generic AMF learning algorithm that we proved a regret bound on, and this distribution, what is it? It's nothing other than the minimax equilibrium strategy in the game that the AMF regret algorithm in general is solving for. And then we'll think about what we need to do if the events are not action independent. Okay, so I'll see you guys next time.